Okay, folks, so let's take that slideshow a little bit further where we talk about ionic nomenclature or naming. So we know that we write the cation first, the positively charged thing, right? And that we write the anion, let's write that in there, anion last. Now that anion can be a polyatomic. Actually, if you noticed, ammonium was a polyatomic cation. So you have to really pay attention to what anions and cations you're looking at. So the stock example that we had is when we brought sodium and chlorine together like this, and I'm stopping myself from saying it, right? We get an ionic compound, a 1-to-1 ratio of sodium and chlorine, and we call this sodium chloride. And you notice that "ide" ending in the name. It's not always that simple, but the patterns and the trends will be all revealed, I promise. Sometimes we have to use Roman numerals when we go to explain. For example, remember we were talking about copper, right? And there's a 2+ version, and there's a 4+ version. So when we go to name these compounds using words, not their symbols, but their words, we have to say copper 2 and copper 4. But this is only when we're describing it in terms of words. As if we were having a conversation and I was just saying it to you. Nobody would say NABR or NABR. Some students will do that, but let's get to it, okay? Sodium bromide. You name the first thing, and instead of saying bromine, right, and we're just talking about the anion, well, now it's an anion as in bromine, we just lop this off the end here. And we just put the IDE part in. Now we can do that because we were just looking at two elements. But what if we've got a polyatomic? Well, that's going to take a little bit of different work. Now, before I expose this in the slideshow, we think about it. We say sodium. And then what is this? Well, in a table of common ions, CO3, 2- is known as carbonate. So, because it's a polyatomic ion, you call it by its name. Okay, that's kind of special, so we'll keep the whole name there. So we say sodium carbonate. And there you go, there it is. This is just two elements. There's no polyatomic involved. So prediction, iron. I'm going to leave a little bit of space here, folks. And I would say chloride. Except when you look on the periodic table, iron isn't as simple as you thought. If you come over to come over to its ion and you look at iron, iron can have a 2+ version. Well, this one doesn't show it as well. Nope. I'll just go to a regular good old periodic table. There we go. There's more than one charge for iron. When we talked iron, when we were looking, and I gotta get my pen up. Can't be erasing now. There we go. So when we look at these transition metals in here, one of the things I mentioned in a previous lesson is that there are a lot of different charges for these things. Well, that's true. And iron, this periodic table doesn't show it as well, but iron has a 2+ version, it has a 3+ version, and sometimes you'll see it kind of written in here, or off to the edge. So, come back. What kind of gives it away is I know that chlorine is, there's 3 of them, so there's going to be 3 negative charges. So in order for this to be balanced, that's probably the 3+ version of iron. And it is. Do you notice that you have to do this? You have to put in the Roman numeral 3, right? Because there's a different kind of iron. This isn't iron 2, right? This is the Fe3+ version combining with 3 chlorines like this to turn out to be neutral. as an ionic compound. Gotcha. So what else? What do we have to? What are sort of the rules? If you've got two elements, you do the "ide" thing, right? "Ide" with two elements, right? But polyatomic ions, they mix up the naming system. Well, here's one. I'll go with the 3+ version of iron, and if I combine that with hydroxide, which is a -1 version, right? I'm getting FeOH, and I'll need 3 of these. Now remember, you got to put the bracket down, right? Oops. Back you go. There we go. Fe3+, OH-, OH1-, OH1-. And that is neutral. That's what you need to have. Now, when you go to give it a name, you have to say that it is iron 3. And the polyatomic ion gets its name. You have to call it hydroxide. So, comes up not just with iron, it comes up with copper, it comes up with manganese, has many different charges. It's not just one. There's like 4 with manganese. So you got to kind of keep your eye on that. Just want to give you another example. What if you had this? How would you describe that? Well, this is the ammonium. That's a polyatomic ion. So you have to say ammonium. Got to call it what it is. Right? It's not as simple as just having an element. And then you say hydroxide. There we go. Let's take an example. Let's say you had copper and you had that formula, copper oxide. Okay, which copper? Well, oxygen has a 2- charge. So, if it's coming together in this proportions, right, it's a sneaky way to know that you must be talking about the 4+ version, because that is neutral. Now you have to name it properly. So you say copper. Oops, spell it proper. Copper. And then 4. And you don't have to put the hat and the foot on like that. I just do it. I'm just more traditional. And then you say oxide, like that. Okay. We've seen last example. You saw KMnO4, and that is potassium. And this is known as permanganate. So you have to call it what it is. There's only one form of potassium. Potassium is always just +1, right? And permanganate, KMnO or MnO4 is -1. So they're balanced, right? That's what you wanted for them to be neutral. So if it's 2 elements, you put in the "ide", right? And if you've got a polyatomic, right, you have to follow the rules of what the polyatomic ion's name is. Okay, so here's a little sort of try this to provide the ionic compound formula. What you want to do here, and I'll do a few of these, and then you can pause the video and do your own, looking at the charges. Now, in your digital textbook, there's a table of common ions, or you can look up table of common ions in the previous video. There's a screenshot of one. You can find it pretty easily on a browser. I'm going to add that also to the Google Classroom. But potassium fluoride, what would the formula be? Well, potassium's symbol is K, and I know potassium's +1. It's in that first chemical family. And I know that fluorine is a halogen. Well, that must be it. KF. 1 atom of potassium, 1 atom of fluorine. Got it. Magnesium phosphide. Okay, so for phosphorus, you look on a sec here. Phosphorus sort of want to think about where it is. Now, call up a table of common ions. There we go. Just going to make sure I have a table of common ions up. And you want to take a look at it and say, okay, so what's phosphide, right? Well, that sounds like phosphorus. So take a look in your periodic table, and we'll go back a little bit. Now you see this is a good periodic table, but it doesn't show these charges, which can be a little bit annoying. So, when you look at the charge of phosphide, right, in an ion chart, you can look it up pretty quick, right? And phosphide, look where phosphorus is, right here, right? And we know that these are our three. These ones have a 3- charge in this group. Actually, you can only kind of go down about this far, right? So, kind of we're doing this and saw this pattern, right? Just like on the other side of the periodic table, we saw these were +1 and these were +2, and then we just kind of avoid the transition metals because there's more to talk about there. But with these trends, let's go back. Magnesium is 2+, phosphide is 3-. Now, that can be a little challenging, right? Write your magnesium, 2+. Now that's phosphorus, but we're saying phosphide, right? We leave the us part of the name off, which can throw you. And if you do the crisscross little trick, which is nothing more than a trick, we've got Mg3P2. So why does that work? I always have to point out why this works. The lowest common multiple of 2 and 3 is 6. We needed 3 magnesium cations to even out, oops, it's trying to zoom in on me there, with our phosphide 3-, 3-, 6+, 6-, neutral. Okay, so Mg what? Mg3. There we go. Mg3P2. Now, not going to do all of them. Come down to lead 4 oxide. You know, lead 4 has a +4 charge, and that oxygen has a 2-. Okay, you can do the crisscross technique, or you can say lead is strong enough on its own. I'm probably going to need 2 oxygens. Why is that? Pb4+, O2-, O2-. Even. Okay. Below you'll see subscripts. You'll see groups. For example, that means NO3 as a group twice. Now, look at your table of common ions in a case like this and find out what the charge of nitrate is. Because there's different forms of lead. Lead's another one that can have multiple oxidation states. So, skipping to the end, I think, well, if I've got nitrate, and I got 2 of those, in order for this to be balanced, that lead must be, +2. That's what would give us an even charge, right? But aside from that, how would we name this, right? Well, you needed to know this because this is lead 2. So we would say lead 2. Gotta put it, well, you don't have to put it in brackets, oxide, like that, just because I'm running out of space a little bit. Lead 2 oxide. Okay. Have a little bit of fun with these, and if you have any questions, check back in with me. Because, ladies and gents, that's the end of how to do some simple ionic naming and a little bit of balancing thrown in. Cheers.